Everybody. So as promised at the end of the last lecture, I'm going to review basic complexity analysis so that we can make sense of what was on this slide here. Okay, so the complexity analysis that you learn in first or second year, unless you're in a really hardcore computing science program, it's basically just a counting exercise, right? That's all you're doing. So all you're doing is counting how many elementary operations does an algorithm have, right? An elementary operation is just an operation that takes a constant amount of time to complete. That's it, right? So you can list the elementary operations, right? So if you do addition, if you do arithmetic with the numeric types, then we consider that to be an elementary operation, right? So 1 plus 1. If you compare two values using less than, greater than, equal to, right? Elementary operation. Loops are a bit funny. I'm just going to say that whenever you see a for loop, a normal, everyday, vanilla for loop, I'm going to call that the loop part, the loop control part, one elementary operation. It's actually more than that, but it turns out it doesn't matter. Okay, so if you have an if statement, you've got if, some condition, else, if, some condition, else, if, some condition, else. Then jumping from the if to the else if to the else if, those all take one elementary operation. So that's called branching, right? Evaluating the condition might be more than one, might not be constant time, may not be an elementary operation, but the jumping from the branches is a single operation. If you get or set a single array element using an index, that's elementary. That's an elementary operation. Assignment, so x equals some value. The assignment part of that is an elementary operation. Break and continue, a return statement, or calling another function or method is all considered are all considered elementary operations, right? You have to be a little bit careful when you're counting operations because sometimes something that looks like an elementary operation isn't, right? But we're not really concerned with those right now. Okay, so if you have an algorithm or a method or a function and you want to know what is the computational complexity, you just start counting elementary operations, right? So you look at each line of code and you ask yourself, how many elementary operations are on this line of code, right? After you've done that for every line of code, you come back and you say, how many times does this line of code run? How many times does the next line of code run? And so on, and so on, and so on. Right? So here's an example of so this is written using pseudocode, right? So this is not any programming language. This is just some generic description of an algorithm, right? So here's a function that swaps two array elements, right? So it takes in an array ARR, right? And it swaps ARRI with ARRJ, right? Switches the two elements. Right? So you start to write down the algorithm, right? So I make a temporary variable, right? I remember the value of one of the array elements. I assign to the array element I just remembered, right? And then I assign to the other array element, and we're done. So you just look at that thing and you say, well, how many elementary operations are on each line, right? So there's an array access. There's one, right? There's an assignment. So there's two. Here there's two array accesses plus an assignment. So that's three, right? There's one array access plus an assignment. So that's two, right? So that was pretty easy, right? Step two, how many times does each line of code run, right? Well, in this particular algorithm, it's dead simple. Right? Each line of code runs one time, right? So what is the total number of elementary operations required by this function? You just take the number of operations per line, multiply it by the number of times each line runs, and sum. So that's a total of 7, right? 2 elementary operations, line runs once. 3 elementary operations, line runs once, right? 2 runs once. Total 7. So it's easy peasy, right? Things get a little more complicated if you have a loop, right? So here's a function that sums the elements in an array, right? So how do you figure out the computational complexity? Well, just start counting elementary operations, right? One assignment, one operation. This is a loop. This is a regular plain old loop. So I'm going to say that this line only has one operation. It's not exactly true, but I'm not going to go into the details of how you evaluate exactly what happens here. Here, there is an array access plus a sum and assignment, right? So we're going to count that as 2 operations. So that's easy. Now, how many times does each line of code run? Right? Well, that runs once, right? We're going to assume that the loop control part here just runs 1 time. Again, not exactly true, close enough for our purposes. Right? Now this line's inside the loop. So how many times does it run? It runs, well, however long the array is. Right? So however many elements are in the array, that's how many times that line runs. Right? How many operations are required? Take the number of operations per line, multiply by the number of times each line runs, and sum. Right? So 1, 1, and 2, 1, 1 in array length. So 1 times 1, plus 1 times 1, plus 2 times the length of the array. Right? So you get a total of 2 plus 2 times the array length. Right? And typically, you give the array length a name, like n. Right? And so what you're often told is, in an introductory computing course, is that the size of this problem is proportional to the size of the array. Right? And so we're going to call the size of the array n. And so it becomes 2 plus 2 times n. Right? That's the number of elementary operations required. Right? And if you look at that and stare at that for a second, you say, yeah, that makes sense, right? Because if I need to sum n elements in the array, then I'm going to have to perform something proportional to n. Right? So that looks like it kind of makes sense. That thing right there, that 2 plus 2n, is called a timing function. Right? So the number of elementary operations required by an algorithm is just a function that depends on the size of the input. Right? And the function is called the timing function. Right? So for the sum algorithm, we say that the timing function, you can call it whatever you want. F of n, t of n are both common. Right? It's just 2 plus 2n. Right? And then at some point, you were told, hey, there's this thing called big O notation. Right? So we say that big O of f of n is in big O of n, right? Or is an element of, or whatever you want to call it, right? So O of n is called the complexity class, right? And this function f of n is part of this complexity class here. Sorry, O of f of n, yeah, that's fine, right? All right, so exactly how you go from the timing function to big O, right? I don't know what they told you. What did they tell you? How do you go from 2 plus 2n to O of n? Yeah?
They said it was the fastest growing term.
That's all they told you? Okay, so that's not exactly how you go from f of n to O(n), right? So to actually go from f of n to O(n), you have to look at the mathematical definition for big O. Were you ever told what that was? Yeah.
They mentioned it's like some constant times a variable will always be an upper bound for the.
Yeah, so that's a description of it. Did they actually give you the mathematical definition of it, though? So did they ever tell you the following? Where is it? Sorry, I just have to track down this web page. Where is it? Bash, here, complexity. That equation there is the formal definition for big O of n, right? So for some function g of n, right there, right, we say that f of n is in big O of g of n if there's some positive constant c and some constant n0 such that that equation is true. Right, so that's the formal definition. Once you have the formal definition, you can go to the, starting from there, you can actually figure out how do you go from f of n, the timing function, to big O of n. Right? So for our purposes, not required right now. Right? If you want me to talk about it, I can do it sometime. I'm going to ignore that part of complexity right now. Right? But that's all that complexity analysis is. You're just counting elementary operations. Right? So it basically becomes a big bookkeeping exercise. Now back here, we've got a recursive algorithm. So things are a little bit different. Right? So that t of n is my timing function for the recursive algorithm, for a selection sort. Right? So what is this thing saying here? Right? So this is saying that for, let's look at selection sort once again. There's our recursive version of selection sort. Right? So we've got an algorithm here. There's t.size. So getting the size of a list, we can say that's one operation. There's a comparison here. So that's 2. There's an if statement, so there's a condition that has to be evaluated here. Sorry, so there's possibly a branch. So you could argue that that's 3 operations right here, right? That thing there. So what's the complexity of min to front, right? So I can go to min to front and count the number of operations if I wanted to. Again, it's recursive, so it's a bit of a problem. But if you think about it for a second, right? To move the smallest element in a list to the front of the list, I look at each element in the list, find the smallest one, and move it, right? So that's going to take a number of operations that's proportional to n, right? So in other words, that step there is in big O of n, right? And now finally here, I've got selection sort, right? So I'm calling selection sort with a list that's 1 smaller than the original list, right? So my timing function for selection sort, right? T of n, that's the number of elementary operations needed by selection sort, right, is equal to, well, I have to selection sort a list that's 1 smaller, right? So that's equal to t of n minus 1, right? Because t is the amount of time it takes to selection sort something, right? Plus the amount of time it takes to move that element to the front of the list, right, which is in big O of n. Right? And now the question is how do you go from that down to O of n squared, right? And so this is what's called a recurrence relation, right? It's a recurrence relation because the function here depends on itself, right? So the definition here is actually recursive. So t of n. So we've got t of n. So I'm going to change the variable name temporarily, right? So I'm just going to call it t of u. So that's equal to t of u minus 1 plus on. Right? That on's annoying, right? So I'm going to replace the on, sorry, O of u. T of u minus 1. This marker's not working so well, hang on. Plus u, right? So in other words, I'm going to replace big O of u with just the u itself, right? If you go back and look at the definition of big O, it makes sense because big O of u just says that there's some constant times u plus some constant, c times u plus some constant is always less than some other function, right? In other words, I'm just going to, all I care about is that this is proportional to u, right? Okay, now I've got t of n minus 1. T of n equals t of n minus 1 plus n. Right? And you say, well, how on earth do I solve this? And you say, well, if I knew what t of n minus 1 was, I'd be gold. So what's t of n minus 1? Well, that's t of u. So if I take the n minus 1 and substitute it for the u, what do you get? Right? So n minus 1 substituted for the u is t of n minus 1 minus 1, right? Plus, substitute the n minus 1 for the u, so n minus 1. Right, so everything in square brackets is just t of n minus 1, right? Plus n. Okay, clean it up a little bit. What does that give you? That gives you t of n minus 2 plus n minus 1 plus n, so plus 2n minus 1. Like that, right? And now you say, well, that didn't really get us anywhere because I've still got this t of n minus 2, right? But you just play the game, you just repeat the game. You say, well, what's t of n minus 2? Well, okay, substitute it back into here. Right? And now you get t of n minus 3, right? T of n minus 2 is equal to t of n minus 3 plus n minus 2. Right? Plus 2n minus 1. And what's that equal to? So you clean it up. T n minus 3 plus 3n minus 3. Right? Now, you just keep on going. but eventually a pattern emerges, right? Hopefully you can see it already, right? If you keep on going, so dot, 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 right? So I'm just going to keep on repeating the process over and over and over again. You get t n minus k plus kn minus k. Right? Yep. Did I screw it up? I probably screwed it up. But anyway, what's going on?
I was wondering what it's like plus 2n minus 1.
Plus 2n. Oh, sorry. Did I mess that up? Oh, I did mess it up. Sorry. Plus 2n. Plus 2n. Plus, sorry, no, that's plus 3n, right? It's correct, isn't it?
It seems like it's right, but then it doesn't match the kn minus k.
Plus k.
Because that, like, if it's like in that,
There's your 2n.
yeah, but then it should be minus 2
Minus 2? Oh, right, sorry.
to match k.
Yeah, you're right. Sorry, minus 2. Okay, so did I do it right on the next step? So 2 of n minus 2 is t of n minus 3 plus n minus 2, right? Yeah. So that's 3n minus 3.
Yeah, it seems like it all seems right. I think.
It's right, isn't it?
Yeah, it seems right, but then it just doesn't match the.
Over here?
Yeah, because then he like. Oh, maybe it is right. Well, but it doesn't make sense. Yeah, because it's n minus k. So if k is 2, then t of n minus 2 should equal. Like it should be equal t of n minus 2 plus 2n minus 2.
Okay, sorry. If k is 2, right? So if k is 2, you should get 2k. All right, maybe we should.
I think it's just like, is the k on the end not supposed to just be the sum of all the numbers less than k?
It might be. That's why you always have to work out the pattern.
Does the k even matter though?
Oh, the k will matter in a second. It'll matter in a second. So let's keep on going one more step. Maybe it is the sum. I don't know. I don't remember. Now the marker's not working. I don't suppose anybody's got a whiteboard marker on them. May I use it? See, this is why you never do stuff on the fly. I always screw it up. Okay, so what do we got? We have t of n minus 3 plus 3n minus 3. Okay, so play the game again. T of n minus 3 is t of n minus 4 plus, plus n minus 3 plus 3n minus 3, which equals t of n minus 4 plus 4n minus 6. Thank you. You were right. And so on and so on and so on. Right? I guess we better do one more just in case. So t of n minus 5 plus n minus 4 plus 4n minus 6. So t of n minus 5 plus 5n minus 10. Okay, so you're right. That's equal to dot, 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 dot. T of n minus k plus kn, and that 10 is
Minus the sum from 1 to k minus 1.
it really the sum?
Yeah. Because you're getting, like, on the next term, you're going to get n minus 5, so it'll add the 5 to that. Or subtract.
Oops, sorry. So the sum of the first I values?
1 to k minus 1 less than k. Yeah.
Sorry, run that by me again.
Just from 1 to k minus 1.
Like that?
Yeah.
Why doesn't that look right? All right. Let's go with that. Okay, and now you ask yourself, does this actually help, right? Because I've still got this funny n minus k in here, right? However, right, you do know what the answer is if the size of the problem is 1, right? If the size of the problem is 1, right, then you know that the amount of time or the number of operations required by the algorithm is some constant number, right? So it's equal to some constant number. So you know that t of 1 is equal to some constant. So I'm just going to call it 1. You can call it c, it doesn't matter in the end, right? So if I substitute k equals n minus 1 into this thing here, right, you get t of n minus 1 plus k kn times n minus 1, right, minus this sum. So k of n, sorry, did I screw it up again? N,
Yeah, you have t of n minus 1
like that.
Yeah.
Thank you. Right, plus this sum, n minus 1 minus 1. Like that, right? Now you know what that is. That's equal to 1, right? That is, sorry, I put the k in. There we go. Plus n squared minus n. Ugh. Right? Plus some funny sum. But this sum here is just the sum of the first n numbers. Right? So that's equal to something that's proportional to n squared. Right? If you remember what the sum of the first n numbers is. Right? So now you've got n squared, you've got an n, you've got another n squared, and all of that's in big O of n squared. And away you go. Right? And so that's how you solve, so that's one way to solve the recurrence relation. Right? You just substitute the equation back into itself. You can go forwards or backwards. So in other words, you can start from t of 1 and then go forwards, go upwards and derive an equation. Or you can start at t of n and come down. Yes?
Why is the something n squared?
It's just you just have to remember what the sum of the first n natural numbers is.
Is that just like a
It's one of these things that, yes. So in the complexity analysis, there's a whole bunch of sums that you're basically given a table of, and you just remember that it's these sums sum to whatever. Yeah. It's actually worse than that. There's something called the master theorem. So the master theorem is basically a theorem that tells you if your function looks like this, the complexity is equal to this. So you can Google the master theorem and find out how that works. Right? Yeah, but that's how you go from this recursive function down to O(n) squared. Hopefully I did that right. And I probably picked like the worst example to do because of that awkward sum that comes in. Right? But that's what ends up happening in a complexity analysis course. Right? You end up working through these sums and recurrence relations like this, right? And then after you learn all of that, they say, hey, there's this thing called the master theorem. You can just look up the answer. But yeah, that's the base. That's how. That's where this slide. That's how you get the answer that's on this slide, right? Going from that step to that step there, right? I'm never going to ask you to do that in this course, but you might. If you take the algorithms course, you might have to do this sort of thing. I think. It's unclear where they teach you how to do this in the curriculum. Right? Yes?
In your last couple lines, you went from you subtracted the sum and then you went to adding the sum. Does that change anything?
Subtracting the sum? Oh, no, sorry. Yeah, actually, I guess you should be more rigorous here. I'm sorry. That is a minus, right? So you really do need to be more rigorous in the final assessment here. If you subtract, when you actually do the sum, it's n squared over something.
I think n squared minus n over 2.
Yeah. So it's n squared, yeah. So you end up with something times n squared, right, as part of the final answer. Yeah. But yes, you really ought to be more rigorous there. All right. Yes?
So big O n squared is proportional
No, sorry, I really shouldn't have written that. Sorry.
Is that what it is?
Yeah. All right, we'll do this more rigorously.
Sorry.
It's fine. That's the sum of the first n over 2 natural numbers, right? Which is n minus 2 times n minus 3 divided by 2, right? So you're going to get n squared over 2.
Oh, I see.
So you have n squared minus n squared over 2, so you get 1/2 n squared. And that becomes big O n squared.
Okay, that makes sense. Thank you.
Nope. Hopefully that's right. I don't actually know if it is. I made up this slide in like the last 20 minutes before class. So, all right. Moving right along. Okay, so we want to talk about, so that's all for the lists for the time being. Now we want to go to sets. Where's, here. Okay, so sets you probably haven't seen unless you've programmed in Java or Python before. But if all you've done is C, then you've almost certainly not actually done any work with sets. So a set, it models the mathematical notion of a set. Right? So in math, a set is a collection of unique elements. Right? So no two elements are equal to one another. Right? And you might ask yourself, so why do I want to keep a collection of unique elements? Right? And so it turns out there's lots of reasons why you might want to do this. Right? So membership testing is basically, does a set contain a value? Right? And it turns out sets are very fast at answering that question. Right? If you have a list and you want to know, does the list contain a value, you have to look at all the elements in the list. Right? So it's always big O. It's big O of n unless the list is sorted. Right? For sets, you can answer the question much faster. You can either do it in O1 time, or you can do it in O log n time. Right? So sets are much faster at membership testing. If you have a list and you want to remove a bunch of duplicates from the list, then you can use a set, because the set only allows you to put unique elements into it. Right? And then finally, if you're in the situation where you need to compute a mathematical operation corresponding to set intersection, set union, or set difference, again, sets are useful for that sort of thing. The other reason you need to use sets, or the more practical reason, is if you want to use this thing called a map, then you need to know how to use a set. So maps will be the next lecture. Right? All right, sets are a bit weird if you're used to using arrays or lists. Right? So with an array or a list, you can get a particular element out of the array or list by using an index. Right? So with sets, there's no indexing. Right? So right away, if you're really used to working with arrays, then working with a set becomes a little bit unnatural. Right? Because there's no way to get an element out of the set. Okay, so in Java, you actually get to pick between different kinds of sets. Right? So there's not just one, there's several. Right? So there's two main kinds. One's called a hash set. One's called a tree set. So a tree set is a set that keeps its elements in sorted order. Right? A hash set is a set that where you don't know what the order of the elements is. Right? So in other words, it keeps the elements, but it doesn't tell you what the order is. Right? It can change the order as you use the set. Okay, so like lists, sets are generic in Java, right? So you have to specify the type of the element, and the set can only hold elements of the same type, right? So just like a list, you have to use this bracket operator to specify the type of the element. Right? So how do you make a set? Well, you make a set in the exact same way that you make a list, right? So you pick your set type, so I'm going to use hash set, right? What type of element do I want to put in the set? So I'm going to put strings in. Right? How do I make one? Well, you just call a constructor. So new, hash set, type, empty brackets, and then the empty angled brackets, and then the empty round brackets. Right? So that'll make you a new hash set, just like we'd make an array list. And just like with array lists, you can't make a set whose elements are primitive. Right? So if you want a hash set of int, you have to make a hash set of big I integer instead. Okay, so sets are, there are fewer methods for sets in general than there are for lists. So for sets, you can make an empty set, so you call a constructor. Right? You can ask, is the set empty, with the isEmpty method. Right? The size method tells you how many elements are in the set. Right? To add an element to the set, it's add again, right? Just like with the list. Now add does something special though. Right? So sets only hold unique elements. Right? So if you add hello once to the list T, that works. Right? So it turns out add returns true in this case. If you try to add hello to the set a second time, then it doesn't add the string hello to the list the second time. Right? Instead, add returns false, right? And the size of your list doesn't change. Right? So it won't add in a duplicated element. Right? You can ask a set, does it contain some value? Right? And contains uses equals. Right? So it takes that value and compares it to every element, not every element, sorry. It compares it to the appropriate elements in the set and tests, are they equal? Right? You can remove an element from the set. Right? So if elem is an element of T, then removes elem from T. If it's not, then it just returns false. Right? And you can copy a set the same way that you copy a list. Right? So if I want to make a copy of a hash set T, just make a new hash set T and just make a new hash set and pass in the set that you want to copy. Right? And away you go. All right, so now when you're picking between your sets, so there has to be a reason why there's more than one set type in Java, right? And the answer is because they have different properties, right? So usually you're going to use hash set, and that's because hash set is extremely fast. Right? So the three fundamental operations with set are add, remove, and contains. Right? Hash set can do all of those operations in O1 expected time. Right? So in other words, it's constant time, regardless of how big that set gets, up to some limits. Right? Which is really surprising if you think about it. Right? So what kind of data structure can you create where you can put something in, take something out, and ask if something's in there, and you can get the answer in constant time? Right? So it's kind of amazing that this happens. Right? You certainly can't do it with a list. Right? One of the drawbacks of using hash set is when you put stuff into the set, you don't know what order they go into the set. Right? So you don't know what order the set is holding them in. So if you loop over the elements of the set, you don't know which order they're coming back out. Right? That might be a problem for some applications. Now your other choice is usually tree set. So tree set keeps the elements in sorted order. Right? Its fundamental operations, add, remove, and contains, they're all fast, but they're slower than hash set. Right? So these are all logarithmic complexity. Right? These are all in O log n. Right? So still a lot faster than a list, a lot faster than an unsorted list, but much slower than hash set. There is a third kind of set that is occasionally useful. So there's something called a linked hash set. So it gives you the benefits of hash set, so very fast, but it also gives you a guaranteed ordering of the elements. So the order is, however you add the elements into the set is the same order in which they're held by the set. Right? So you put an element in first, it's the first element. You put a second element in, it's the second element, and so on and so on and so forth. Right? Now the way this thing works is it actually uses a hash set. Right? That's why it can do this very fast add, remove, and contains. But it also keeps a list or some other collection of the elements that are in the set, so that it can iterate over them in a fixed order. Right? So this thing effectively, it takes additional memory that's proportional to the number of elements in the set, right? Which you don't always want to pay for if you have a very big set. Okay, so there's no indexing in a set, right? That means you can't write a regular Java for loop to loop over the elements of the set. Right? So you can't write for int I equals, I is less than whatever, right? And then try to use indexing to get the elements out. If you want to loop over the elements of a set, you can do so using a for each loop. Right? Okay, so one of the useful things that sets let you do is remove duplicated elements. Right? So if I have a list and I want to find all of the elements that occur one or more times, then you can use a set to either identify or remove the duplicated elements. Right? So imagine I've got a list of student account names. So these would be your Queen's net ID. Right? And I want to find all of the unique net IDs that I have in this list. Right? Rather than looking at the list, right? So you could look at each element in the list, compare each element of the list to every other element of the list. Right? If you do that, that takes time proportional to n squared. Right? Instead, I can take the list and pass the list to the hash set constructor. Right? And the constructor will create a set that has only the unique values in that list. Right? So now I've got a set of unique account names. Right? If I want to turn that back into a list, it turns out you can make a new list and pass that set to the list constructor. And the list constructor will copy all of the elements out of the set and put it into the list. Right? And so that's the easy way of removing duplicated elements from a list. If you want to know the unique account names in sorted order, just use a tree set instead. Right? So pass the list to a tree set, and tree set will produce a sorted list of unique account names. And if you want to maintain the same ordering as the original list, that's when linked hash set becomes useful. Right? Because linked hash set will keep the order of the elements that are in that list. Okay, so that removes all the that gives you the unique account names, right? What if I want to find the duplicates, right? So to find the duplicates, you use two sets, right? So I'm going to start out. So remember, CS account, that's a list of account names. So I'm going to make two sets, right? The first set will be the unique accounts. The second set will be the duplicated accounts. Right? So now you write a loop, and you loop over the elements in the list. Right? And now I try to add the element to the unique accounts. Right? So add the account to the set of unique accounts. Right? Add returns true if that account name is not in the set already. Right? It returns false if it's already in the set. Right? So if I exclamation mark, unique account add, right? So if I can't add the account name to the unique accounts, right, then it must be a duplicated account. So just add that account name to the duplicated accounts. And when that loop is done, you've got the set of unique and duplicated accounts. Right? So in a picture, this is what it would look like. Right? So I start out with my list up here. I'm going to loop over the list elements, and I'm going to try to add them to a unique account. Right? So there's nothing in unique account, so the first element goes in. Right? The second account name is not in a unique account, so it goes in. Right? And so on and so on. Right? Now when I get to the next name, right, that name is already in the unique account set. Right? So it doesn't get added again, and add returns false. So I know now I have to put it into the duplicated account set. Right? And then finally, the last one, it already appears in unique accounts, so we don't add it to the unique accounts again. Instead, you add it to the duplicated accounts. And there are your two sets. Okay, so the set union if you have two sets, then the union of the two sets are just all of the elements that are in the two sets with the duplicates removed. Right? So suppose I have a list of a set. Suppose I have a set of students who have completed assignment 1 and a second set of students who have completed assignment 2. I would like to know who's completed either assignment, right? Either both or one of the two, right? And that's where you would compute the union, right? So if I have a set S1 and a set S2, then S1 add all S2 transforms S1 into the union of S1 and S2, right? So this is called a destructive union right here, right? Because it changes S1. Okay, if I don't want to change S1, right, then it's easy. you just make a new copy of S1, right? So I'm going to make a new set called either assignment. I'm going to copy the first set. You can copy the second set as well, it doesn't matter, right? Then I'm going to use add all and try to add everything that's in S2 to S1, or sorry, to either assignment. Right? So if you need a picture of that, there's your set. There's your original set S1. There's my new set that's a copy of S1. Right? Now all we're going to do is we're just going to loop, add all just simply loops over the elements of S2 and tries to add them to the new set. Yes?
I was just going to ask if there's like an overlap between them, we'll just ignore the one.
Yeah, that's exactly what's going to happen, right? So let me back up one step. So when we add all, we're going to look at this name here. We're going to ask, is it in the set? The answer is yes, so we don't add it. Right? We look at this name here. Is it in the set? The answer is yes, so we don't add it. Is that name in the set? The answer is no. Is that name in the set? The answer is no. So they both get added to the set. Right? That's why it's called add all. Right? So that's set union. What about, what about the intersection? Right? So the intersection example would be, I have students who did, a set of students who did assignment 1, a second set of students who did assignment 2. I want to know who did both. Right? So retain all is the method that computes the union. Right? S1, retain all S2, transforms S1 into the intersection of S1 and S2. Right? Again, that's destructive. It's the destructive intersection because it changes S1. Right? So if I don't want to change the set S1, just make a copy. Right? So the set called both assignments is just a copy of S1. Right? Now I'll transform both assignments into the union of that in S2. Right? So retain all keeps all of the elements that are in both S2 and both assignments. Right? So there's students who completed assignment 1. There's my copy, students who completed assignment 2. Right? So retain all. So is this student in this set? Right? The answer is yes, so we're going to keep them. Right? Is this student in this set? The answer is yes, we're going to keep them. Right? Is this student in this set? The answer is no, so we're not going to add them to this set. Is this student in this set? The answer is no, so we're not going to add them to this set. Right? Is this student in the other set? The answer is no, so we're going to get rid of them. Right? Is this student in the other set? The answer is no, so we're going to get rid of them. Right? So you end up with that set. Right? So retain all actually loops over the first set. Right? So it actually loops over that set there. And finally, the difference. Right? So if I want to know who's completed only assignment 1, right? Then that's where you'd use the set difference. Right? I want to take set 1 and I want to subtract all the students who did S2 or assignment 2. Sorry. Right? So remove all is the method that computes the destructive difference. Right? S1 remove all S2 changes S1 so that it becomes the set difference S1 minus S2. Right? If I don't want to destroy S1, make a copy. Oh, sorry. Make a copy. Oh, come on. Make a copy. Right? And now transform the copy. Right? So students who did assignment 1, there's the copy. I want to subtract all the students from S2 from this set here. Right? So is this name in this set? The answer is yes, so I'm going to kick that name out. Is this name in this set? The answer is yes, so we'll kick that name out. Is this name in this set? The answer is no. Right? Is this name in this set? The answer is no, so we're going to keep them. Right? And you end up with the following. Right? So those are the students who only completed assignment 1. Okay, and so that's it for sets, right? So you can't actually do a lot with a set, right? If you can't actually go in and get individual elements of the set, for example, right? Because there's no indexing operator, right? You can loop over the elements of the set, but that doesn't seem it doesn't seem like that's the thing that's a common operation that you would want to do all the time, right? Now there is something about the sets, about other types of sets. So Java tree set. Okay, so what I told you about in that lecture, I told you about the operations that are common to all sets, right? But you have different kinds of sets. And so that means that maybe these different kinds of sets, they can actually do things that the other sets can't do, right? And that turns out to be true. So a tree set, remember, that's the set that keeps its elements in sorted order. So you can do stuff with a tree set that you can't do with a hash set, right? Like, for example, I can ask for the first element in a tree set, right? Because a tree set keeps its elements in a fixed order, right? A sorted order. So that means there's always a first element if the set's not empty. Hash set says it can change the ordering of the elements whenever it wants, right? So it doesn't make sense to ask for the first element, because if you call first twice in a row, you might not get the same element back, right? Now, if I get the first element, can I get the second element, right? The answer is yes, right? There's a method called higher. So if you call higher and pass in an element, higher gives you back the next element that's greater than the element you passed in, right? So if a tree set keeps all of its elements in sorted order, can you yank out a bunch of elements at the same time, right? So for example, suppose I have a dictionary of English words in a set. Can I find all the words that start with the letter A, for example, or the letter Z? And the answer is yes, right? There's a subset method. So subset lets you pull out all of the elements starting from there, going up to there, right? So for example, I can pull out all the elements in a dictionary, all the words that start with the letter A, by passing in the from element would be the letter A. From inclusive is true if I want to include the from element in the return set. So that would be true. To element would be B, right? And to inclusive would be false. So don't include the letter B in the return set, right? And that would give you back all the words that start with the letter A, right? And so you can get these range operations with tree set, which you can't do with hash set, right? It doesn't make sense in hash set because it doesn't keep its elements in sorted order. So the different kinds of sets let you do different kinds of things with them, right? Tree set in particular does a lot more stuff than other types of sets, right? It lets you do things like return a range of values, which is very useful in some applications. All right, so that's it for sets. Next lecture will be on these things called maps, and then we're going to transition into creating our own types. All right, so I guess I'll see you next week.